Yeah, I don't know how that will work with timing, but I mean,
Okay.
since we are already booked to 8:30, so I guess I can.
You can take your time, no problem. Yeah,
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 so I
there's
can
no
take more
time limit.
than 1 hour then.
Yeah,
Oh,
yeah,
shall we start?
yeah, yeah, please, please go.
Yes. I mean,
Shall we start, Abdullah?
yes,
Yeah,
I
yeah,
can.
yeah. Please introduce. Yeah.
Okay, okay. Hello everyone. Today we have with us Abdullah Hamdi. He's a PhD student at KAUST Computer Vision Lab, IVUL. He also did his master's from KAUST, and he recently won a Best Paper Award at ECCV Adversarial Workshop. Today we are going to discuss not one but two of his papers. Both were accepted at ECCV, and one even received a Best Paper Award at AROW Workshop. So we look forward to the talk, Abdullah.
Okay, hello everyone. Thank you, uh, Mishra, for your introduction. Thank you actually for hosting this series of talks on computer vision, which are dedicated to students, um, or like I would say some people who are early in their career. So we have seen a lot of seminars for experts or big shots in the community, but this is, I think, a very good platform for young people to present their work and connect with other people with the same interests or with similar background. So thank you actually for hosting these virtual seminar talks, and thank you all the organizers for making this happen. So today I'm going to talk about 3D adversarial attacks, or sometimes called physical adversarial attacks on deep learning models. Before I start, here are some of my contacts if you want to connect with me, my website, my Twitter. I'm pretty active on Twitter, and there is also my GitHub account. So this is my group at KAUST. We are Image Video Understanding Lab, supervised by Dr. Bernard Ghanem. We work on computer vision mainly, but also do research on machine learning, autonomous driving, robotics, and so forth. We also are like kind of a family more than a research group, so we also enjoy some activities around here. And yeah, so we are pretty large group in KAUST, and this is a picture of me with Jan LeCun, because everyone is familiar with Jan LeCun is. I met him during one of the AAAI conference in New York this year, just before everything shut down because of COVID. So that was like the end of February 2020. Uh, More than a year ago, I founded fihm.ai, which is a platform, an educational platform to teach about AI concepts. It has articles that are targeted for general audience, and then there are technical lessons that are targeted for people programmers or people who want to learn more about AI, all in Arabic language. And then we have a YouTube channel which has a lot of videos, educational YouTube videos about AI concepts. And also we do some research videos that are more technical and discuss some of the recent papers in deep learning. So this was an overview about me and my group, our group in KAUST, and what I've been doing recently so far. Okay, so we all hear the news that deep learning, or read or being taught in courses that deep learning is the new thing, basically performed better than um, everything so far on the vision, on NLP, and now it's actually crawling to graphics, biology, and even social sciences and so forth. Actually, deep learning started to do some huge impact. This is one of the famous benchmarks, like ImageNet benchmarks we saw over the last like this is old, but like starting from 2012 with AlexNet, deep learning basically was dominating vision tasks. However, what they don't teach in courses is this thing. Even though these models are really great, they tend to have weaknesses. And one of these weaknesses is the very sensitivity to adversarial noise, which is a very special type of noise that if you just add it to the image, or actually people have been applying this adversarial attacks to NLP, 3D vision, and probably any deep learning model that is applied on any domain. You can always find papers that try to do this, and they successfully show that you can break any deep learning model with very small amount of noise added, like here. So I would, regarding questions, you can interrupt me at the end. So I divided my talk into, I would say, chapters. So you see, for example, here, that's an end of a chapter. So once I reach like some end, I can stop and you can just ask any questions.
So
yeah.
we'll be monitoring the chat. So you go ahead. If there is anything, we'll interrupt you so that you don't have to.
Yeah, I can't monitor the chat while presenting, so it'd be very hard for me.
Yes. If there is any question that comes up, we will interrupt you.
Okay,
so
great.
It is fine.
Yes, great. So this is also one of the recent demonstrations of how dangerous these adversarial attacks can, in which like a printed image can actually fool ECCV version 3 detector, which is like one of the standard, I would say, object detectors used in industry. Yeah, so these things just showcase how vulnerable these deep learning models that we rely on frequently. So yes, now we will start the discussion about what are adversarial attacks. So adversarial attacks basically, its objective is to find X bar or X prime, which is very similar to X, which is, let's talk about only image domain for now. So we want to find an adversarial attack X prime that is very close to the original image X, such that the decision of the classifier C would flip. So you can see on the left, this is the main objective used in almost all of the classifiers. This objective is specifically for targeted attack, which means we want to find the minimum L2 perturbation on X, such that if we add it to X, we will find X prime, which will the classifier classify it to L, which is another label other than the ground truth label of that X. And also X prime should be in the permissible range, which means between 0 and 1. So this is how adversarial attacks started by a paper by Ian Gottfella, which is the first author of GANs also. In 2015, this very influential paper, I think it has 3,000 or 4,000 citations. And this objective is very hard to optimize because the condition that the classifier would classify as L is very hard condition. Like it's, you cannot easily project your solution into that domain. And therefore people actually, what they do is they make it as a soft condition, which means they, just like what you do in a Lagrangian multiplier, you basically put it on the objective, you put the condition on the objective with some trade-off parameter or hyperparameter with the main objective. So this is one of the earliest ways to do these, which is called fast gradient sign method, which basically try to make the attack in one step, which means you only do one step of optimization, such that if you projected or if you take the gradient of the loss and you just take the sign of that gradient and then you multiply it with some epsilon, you add it to the to your original image, you get like a new adversarial attack, X prime, and you take that as your final solution. This one is very fast, so it's only one step, one direct step, one backpropagation step to find the gradient. By the way, this gradient is not the gradients that you are doing when you train your network. It's a gradient with respect to the input. So it's the same loss. So you can imagine the loss to be the same cross entropy loss for now. I'll discuss this later. And then you want to basically maximize that loss instead of minimizing it. You just add it to that X, taking the sign of that gradient. However, that gradient is only the gradient of the loss with respect to the input, not the gradient of the loss with respect to the weights. In PyTorch, if you're using PyTorch, you basically create a variable at the input level. You just add that variable to the X, and then you optimize that variable, which has the same size of the image, and that would be your the noise that you're optimizing for. So you can do that even in iterative ways. So you basically keep adding these directions instead of doing it once. And therefore we would have an iterative fast gradient sign method, which is also very famous in the literature. One of also very famous attacks in the adversarial attack literature is what's called Carlini and Wagner. So Carlini is one of the big shots in the field or in the literature of adversarial attacks. He has so many good papers, but this paper of his is the most famous paper. It's actually in a security and privacy conference, but it's very influential in the machine learning and computer vision community. So what they did in this paper, they investigated all of the possible formulations to do adversarial attacks. So they said, you can do it like this, or you can do it like that. Here, they didn't restrict F to be the cross entropy loss. So they will define different Fs here, such that they have the same meaning or the same effect of the cross entropy. And they will minimize a distance between X and X prime. So X plus delta is the adversarial attack, and X is the original image. They did like multiple or many versions of this adversarial loss F. And then they found that if actually this one, sorry, the sixth one, which is taking the difference between the logits. So Z is the logits layer. If you take the difference between the logit of your target T and the logit of your closest contender, which means you find the class label that has the highest logit value, which means your current classifier will classify it as this label. You take that label, specific label, and you subtract it with your target label. You subtract the two logits. You do a reloop on top of that, and then you basically optimize this loss here as F. You also optimize, or you try to minimize the distance between X and X prime. This can be easily done by taking the L2 norm between X and X prime, or taking the L2 norm of delta, which is the noise itself that you're adding. You also add it with some constant C to this adversarial loss, and then you run an optimization, and you basically can get a very good attack. Here in this figure, they show how if you this C is like hyperparameter, you don't know what's the best one. So they show if you increase C, you reach like 100% success rate. You can see here, like at this C, you will reach 100%. However, the problem, if you increase C too much, the noise energy would also increase. So in adversarial attacks, we want the energy noise to be very low, or to be very low, such that you don't notice a difference when you add it to the image, like here. You can see when you add this noise to the image, you don't notice any difference in the image, because then the energy of this noise is very small.
Abdullah,
So,
can the same concept we apply to time series data? The same concept?
So I have seen adversarial attacks, yes, on time series, and they were attacking an LSTM, for example, that processed some language or some speech signals. But yeah, so this basically, this same concept, the same objective is used everywhere to do the adversarial attack. One of the most famous attacks also, the one on the bottom, which is called the PGD, or projected gradient descent, which is used to project the gradient or the sign of the gradient into, so this pi is the projection function. You basically keep projecting your output or the attacked image into some space that is not very far from the original image. So you basically, I will show later on, like in one of my papers, I put it in a simpler way than this. But this is one of the most famous attacks, and it is used as a defense mechanism in what's called adversarial training. So adversarial training is not GAN training, if you are familiar with GAN. That's also called adversarial training, but it's a different context. Here in the adversarial training, our objective is to minimize, is to optimize the weights of the network such that we minimize the expected. Usually when we train a network, we minimize the expected risk, which is called expected risk minimization. We take the average of the loss and we want to reduce somehow the mean of the loss over time. In this formulation, they don't want to minimize the mean of the loss. They want to minimize the expected value of the worst case scenario or the worst loss around specific X. So you can think of X as one training example. And then for every training example, we don't want to minimize the loss at that example, but we want to minimize the loss in the worst case scenario around that example. The worst case scenario is defined by the maximum loss around that example, defined or limited by some epsilon or delta here. Sorry, epsilon. The delta is the objective or the variable that we are adding around every example to make that example very hard. And then we minimize the loss for that specific hard example. So it's very different from what we are very familiar with in expected risk minimization, where we basically just sample some points X and then we do minimize cross entropy, for example, to optimize the weights. Here we have to do an adversarial attack for every specific example to approximate this objective. We do an adversarial attack with like 20 PGD iterations, and then we train on cross entropy for that adversarial attack. And we do this for all examples. So it's very expensive operation because we do optimization and network training jointly. However, this actually proved to be one of the strongest defense mechanisms and produce very strong and robust neural networks. Here are some of the references. So this is basically it. Like this is just a brief introduction about adversarial attacks and what are the most famous papers in the literature. Yeah, so
would it be possible for you to navigate to the last slide? I had a doubt.
Yes.
No, the previous one with the equations. Yes. Can you explain this term being added to XT? This is what randomness. I'm not able to understand this one.
This you're talking about this delta.
In the second equation.
The second equation. So this pi is a projection function. You can think about it as a wall or like a fence that will prevent us to go very far from the original image. Okay. It's like a hard constraint projection. You always prevent the output of this operation to go beyond a specific area.
Okay.
This XT is the image after the previous iteration. So this is iterative update step. We do this iteratively for, let's say, 20 iterations, for example. This alpha is just like a learning rate. It's a learning rate. This is the sign operation. So you only take the sign of the gradient. You don't take the value. You assign all of the values in the gradient to be either 1 or -1, depending whether the values of the gradient, if it's positive or negative. And L is basically the loss that we are optimizing, which is like the ones that are shown here.
Right. Understood. Thank you.
Yes. Yeah. I don't know if there are questions or. No questions?
No, I think we can proceed.
Okay, so we start with the papers that I'm presenting today. The first one here, AdvPC, which is Transferable Adversarial Perturbations on 3D Point Cloud, which was a poster paper at ECCV 20, which was held between August 23 and 28 this year. Virtually, it was supposed to be in Scotland, but it's virtual this year. Joint work with Sarah Rojas, Ali Thabit, Bernard Ghanem. So 3D point clouds are very famous and well-known and useful representation for 3D data in which we treat every point independently, and we analyze the 3D object as a set of 3D points, which is very compact and very easy to handle. It has some drawbacks, like we don't have the connectivity between the 3D points, but it's very common to use it in 3D vision algorithms. In recent years, after the introduction of PointNet, which was the first deep learning method that works directly on point cloud, this opened the door for deep learning to work on 3D, and with the recent introduction of DGCNN also, which is very famous network on 3D point cloud data, which paved the way for so many applications like classification, 3D object detection, and 3D segmentation. However, just like what happened with images, these 3D point clouds have been shown from this paper in CPR 19 to be very vulnerable to adversarial attacks. You can see the red one is actually perturbed or attacked point cloud. And basically the point cloud network is not able to identify this as an airplane anymore. The problem with these attacks are these are very easily defendable, because you can see that these point clouds have some outlier. So if you did outlier removal, you can actually recover the performance quickly. So this paper in AAAI 20 was also tackling the problem of adversarial attacks with point cloud. They showed actually you can 3D print these point clouds attacks, and if you do a 3D scan, you still maintain adversarial attack strength for these point clouds, even after 3D printing and scanning. However, all of these attacks are not transferable. So if you want to quantify how strong is an attack, you can measure the distance or how close it is to the original sample. And then you measure the success rate, which is how many examples that are attacked are successful in attacking the classifier. And then you also can measure how transferable is the attack, how generalizable. So if you take that specific noise and you add it to another network, will it still be adversarial? And this was one of the main points that people in the 2D literature were investigating. So in this, there was also a paper from ICCV 19, which did defense on point cloud, they did it very simple ways, like simple random sampling or outlier removal or some denoising network, like upsampling network. They showed actually it works very well as a defense mechanism for point cloud. So in this paper in ECCV 20, we're trying to produce a stronger attack that can bypass many of the defenses introduced so far, and also can be transferred to other networks. So if you attack a point net network, you can actually take that attack and give it to any other network like PointNet++ or dynamic graph neural network, and it will still be adversarial. Yes, so this is our attack pipeline. We want to attack a classifier F using some perturbation or additive noise on some input point cloud, such that if you add this perturbation to the input point cloud, you will get, we want to utilize two adversarial losses. One, the regular adversarial loss, which was usually used in the literature and actually used in the baseline, in our baseline from CPR 19. However, we also utilize a point cloud autoencoder to create another type or a different type of adversarial loss, which is basically an adversarial loss after reconstruction with an autoencoder. So basically, we just balance these two losses. One, the regular adversarial loss, and one is after the reconstruction, to obtain an attack that will attack the classifier F, but also can transfer to different classifier networks. So this
Abdullah,
Yes.
Abdullah, I think one question from Bautista. Bautista, can you please unmute yourself and go ahead?
Yes.
Hi. Yeah. So I have, well, one of the questions, one is a rookie question about the perturbations.
Yes.
So the perturbation is just spreading the points, or could it be like alter the size or the color to be part of the
So the color is just for visualization purposes. It's a colorless, sizeless points. A point cloud is just an XYZ coordinate set of coordinates. Yes.
So, about that, I think I missed some part. Maybe that why is a better choice using cloud over meshes, for example?
Yes, so this goes back to here. So yeah. Point cloud, actually, if you look at the papers on 3D vision that works on point cloud, they are much more than the papers that work on meshes or voxels, for example. Mm-hmm. Because you can also represent 3D shapes as voxels, which means like pixels, but in 3D. Like you divide the 3D space into cubes, and then every cube either is filled or not filled, for example. Mm-hmm. This is what's called voxels. And there is also the mesh, as you said, which is very famous in the graphics community. But in 3D vision, it was initially hard to do deep learning on voxels because voxels have a cubic complexity. So if you want to do a very high resolution shape, for example, you would need 100 or 200 voxels times 200 times 200, which will basically explode the memory. So people were looking at point set or point cloud because it's very efficient. You can represent this shape with only 3,000 numbers, which are basically 1,000 point cloud, and every point cloud have 3 numbers, which is X, Y, and Z. So it's very compact. It's not like, compared to a mesh, you have also the vertices connection or the surface information, which is also compact, but that one has a problem of how would you process connectivity independent of the points. Actually, very recent works started to work on meshes directly. So now you can have mesh network. I think there is a paper called Mesh CNN, and there is a paper called Mesh Network, which can work directly on point cloud, but this one came first. PointNet came first, which is basically doing convolution on the point cloud directly.
Excellent, thank you.
Yes.
Yeah, go ahead, Abdullah. Go ahead. Yeah.
Yeah, so we're basically trying to add just noise, and we are optimizing that noise to make it adversarial to work on. Yeah, please, everyone mute. Okay. So we want to optimize that noise to make it adversarial. This is the objective that we're following, which is the same objective that was followed before in the literature. We only added one condition, which is the adversarial loss on some reconstruction G of the X prime. So X prime is just like before, it's the adversarial attacked point cloud or sample. F is our classifier or the logits layer of our classifier, and G is the autoencoder. So this is how we solve it, which is also very similar to the literature. We are only adding this part, which is with some hyperparameter gamma. This is the only hyperparameter in our paper. And we are basically doing a trade-off between a simple or baseline or basic adversarial loss and some adversarial loss of the reconstruction. And we want to optimize that. And we want to make that trade-off works well, such that we not only succeed in attacking the network, but also we create a stronger attack that will generalize to unseen networks. Yeah, as I said, this FT, or this is the adversarial loss from the Carlini and Wagner paper, which is shown here. This is the hyperparameter, as I said. Epsilon is just a norm budget. So we solve using a projected gradient descent. We always project into some LP or L2 or L infinity sphere with some size. Because if you increase this epsilon, you will always increase the success rate. So as we will show later on, this is like a control parameter. You should sweep with different values and do a plot for a fair comparison. So this is the update step. We do projection into L2 sphere, which is a sphere, and L infinity sphere, which is basically a cuboid around your point delta. So in experiments, we experiment with ModelNet 40 data. This is like ImageNet on 3D, or the most famous 3D data set, along with ShapeNet. We experiment with 4 networks on point cloud, PointNet, PointNet++, 2 versions, and dynamic graph convolutional network, DGCNN. Here are some examples of our attacked point cloud. You can see that it's very hard to notice, but these attacks actually can flip the prediction, as you can see here in these examples. Like the bottle would be classified as table, the airplane would be classified as bottle, and so forth. So it works very well. It works as a targeted attack, which means you pre-specify the target of this bottle to be monitored, and then you do the optimization, and you get this one. Or it can be untargeted like this one. Here we show some results. So every row in this big table, this is the only important table like in the paper. So every row here is basically an attack on a specific victim network, as you can see on the left. Every column is the evaluation. So we do the evaluation independent of the attack. So if you attack PointNet, you can evaluate on PointNet or PointNet++ or DGCNN. We use 2 different epsilon infinities here, which are the budget that you're allowed in the attack. And we report the attack success rate in 3 methods. So the 3D adv is one baseline from CPR19, KNN is one baseline from AAAI 20, and AdvPC is our paper. And you can see that we are always getting larger attack success rates than the baselines, especially for the networks that are not used in the attack. So for example, in this one, we get 64 compared to 14 or 31. Here we get like 46% success rate compared to 9 and 11. We noticed that we are a little bit less than the baseline on the same network that we do the attack, but this is the cost of generalization. In order to, it's just like doing training and testing. In your train set, you don't want your accuracy to be 100%, right? We want the test set accuracy to be 99 or 98. We don't want our train accuracy to be 100% because we don't care about training set. We care about the test set. This is the same. So here you can imagine that the victim network is just like a surrogate network, and you want our attack to be generalizable to unseen networks. So we can actually do the plot, not only for 2 epsilons, but we change the epsilon and we plot the success rate. So this attack was on DGCNN on the left. You can see that the bigger the norm, the stronger the attack, it reach 100%. And then if you take that attack and give it to other networks, you can see that our attack in green always get better accuracy, better success. So success rate, you can think about it as the inverse of accuracy. So if your accuracy, it's not exactly, but you can think about it like that. If your accuracy is 90%, that means your attack success is somehow maybe 10%. If your accuracy is 0, probably your attack success rate is like close to 100. Okay. Yeah, so this is how you would think about success rate. So we do this.
So Abdullah,
yes.
Yeah, when you're doing targeted attacks, how do you decide the perturbation? When you're doing, let's say, a bottle, you were able to classify it as a table or whatever. So
yes.
At that point, how do you determine the perturbation?
It's the same. Like the objective we showed can work on targeted or untargeted. So you can always...
How are the values for epsilon?
So the values for epsilon, you don't know it before the attack. So this is like a fixed hyperparameter for every attack. You should always determine this epsilon before you start the attack.
Yeah, see, because when you, can you go to the slide where you have, I think, bottle classified as monitor, maybe?
Yes.
Yeah, that is where I had, yeah. Bottle classified as monitor. So you don't know the value of epsilon at that point? Okay.
No, so basically, as you see in these experiments, like you don't know the value of epsilon for that specific example. You just pick one epsilon and then you do the attack. And then you just sweep that epsilon for all of the examples. And then you plot this plot, which is like, it shows you how strong is your attack. So
then
actually,
without knowing that, how will you target? Let's say, if you want to classify bottle as whatever, a table, so you should have some prior knowledge, right? Not required?
You don't, so, yeah, I understand your concern. For this type of PGD attack, you don't know the epsilon. So you just pick one randomly. It might work, it might not work. However, like the Carlini and Wagner formulation, which is, I think, showed very early on, in this one, you don't need, so it's just a hyperparameter C that you feed it. You can always pick very large C and you are very sure that you will succeed in your attack. However, this is not, we use PGD because it's somehow fair, because we are comparing against 2 baselines. So we thought it was fair to use only constant epsilon. So there are other papers that try to do this like adaptively, change epsilon for every example. But in this work, we just keep it constant.
Okay.
So we actually can just average these attack success rate, and then we form what's called transferability matrix. We basically, you can see that every network can attack itself very strongly. So yellow diagonal value means every network can attack itself. However, off diagonal values indicate transferability. You can see we have 3 matrices here. Our method is the one on the right. can see it's very bright, which means the attack can transfer to different networks. If you just average all of the off-diagonal values, we get a score for overall transferability. You can see that our get like 24% compared to 8 and 11 for two baselines. Here we evaluate the defense, our attack against different defenses from the literature. We can see, for example, that our method have always a better attack success rate on defended networks. And it's actually by up to 38% improvement over the baselines for this specific defense, like simple random sampling. Yeah, so this is basically this paper. And it has code online, TensorFlow.
Yeah. When you say Abdullah, when you say transferability, what exactly are you transferring? Like which quantity?
So transferability is just like when you create the attack like here. So the black one is the clean sample. When you attack it with the blue, or you obtain this blue one, you just take that blue shape and give it to different networks other than PointNet. Give it to PointNet++ and all the other networks. And you measure the accuracy and the success rate of that attack for the other networks, not for the network that was used in the optimization.
Okay. Got it.
Yes, so this is basically it about this paper. If anyone has questions, please ask.
Yeah, so I don't know whether you want to take it now or later, but let's go. Zara, can you unmute yourself and go ahead? Okay, so she had a question. She is here anyway. She is working on her master's thesis and she would like to know how to find error loss or the gradient. Is it by using built-in libraries or do we have to write it ourselves? Zara, you can unmute yourself and go ahead. I don't know, Abdullah, you want to take it now or at the end of the presentation?
Yeah, I can answer this now.
Yeah. Zara, please unmute yourself. Yeah. Oh. Okay, maybe some issue with the mic.
Maybe Abdul can answer that answer.
Yeah, so I'll just repeat the question for you. Hi, I am very new to computer vision and deep learning. My master's thesis will be on image classification. I want to know how you can find the error loss or the gradient. Is it by using built-in libraries or do you have to write it by ourselves?
No, you don't have to write anything yourself, obviously. If you're using PyTorch, you just do x.grad, you will get the gradients in the input. As long as you just keep it to be the tensor PyTorch center to requires grad, it will always compute the gradient with respect to the input. If you're using TensorFlow 1, for example, I'm not very familiar with TensorFlow 2, which is actually, this project was built on TensorFlow 1. You can basically assign a new variable, delta, which will be the attack itself. And you just define some constraints or projections on that delta. And then you do a simple optimization with TensorFlow, the same like session training where the optimizer would be optimizing not the weights of the network, but you use the variable itself as the variable of the optimizer. And then you run the session for different like iterations, and you will get your noise, your adversarial attack.
Yeah, Zara, I think please follow up if your question is answered or not. Please also reach out to Abdullah. You can also reach out to him via Twitter, email. So after the talk also you can.
Sure. The code for this paper is, again, it's here. So
good.
You can find everything about this paper in that GitHub repo.
Good. So Abdullah, what were the reviewer comments for this paper? Anything significant that you can remember? Did they ask you to?
So it was, I mean, it was accepted at the end, but they were concerned about how would that be realistic, or would that attack happen on, let's say, a LiDAR sensor or something like that. So this was not focused more on like application. It was more like an improvement from the methodological point of view for the two baselines that are in this. Actually, there are now very large, I wouldn't say very large, but there are several papers on point cloud that are doing adversarial attack and adversarial defense. In this ECCV, I think there were already 4 other than this paper. So yeah, this is a growing small subfield from 3D vision, which is focused on adversarial attack and defense.
Good.
So moving to this paper.
Yeah, I had a quick question. If
Yes.
that's okay.
Go ahead.
Go to the results slide where you had a table for the attack table.
Yes.
Yeah, so actually in this table, I noticed that for the epsilon 0.45, which is more than 0.18, in the first, the PN section, like
Yes.
the attack success is less in the epsilon 0.45. Is there any intuition for that? Like in all the cases, it is less than the smaller epsilon of 0.18.
It's smaller on the other networks, not on the target networks. You see the point? It's smaller on the other networks. If you use PointNet and you move it to PointNet++, just because the epsilon is larger, it doesn't mean it will transfer well.
Yeah.
You see my point?
Shivam, follow up if you haven't understood, follow up, it's fine.
Yeah, actually, I mean, I was thinking that because the epsilon is larger in the second case, maybe, it is easier to create attacks. Maybe
yes, you're right, you're right. You are right.
It doesn't essentially mean that it is transferable. Yeah, I get the point now.
Yeah, so if you look at, if you use PointNet++, this MSG, and you look at MSG here, you can always find it's bigger, the attack success on the same network. But if you look at different networks, it might be better, it might be worse. It doesn't necessarily imply just because it's bigger, it will work on other networks. Does that answer your question?
Yeah, I got it.
Okay.
Shivam, you can just give a brief background of yourself, of what you're trying to do in your job or work, so that Abdullah knows what you are trying to do.
So, I mean, I just finished my undergrad.
Very good.
And right now I'm working as a research assistant at Yale. So I'm not directly working on adversarial attacks, but I'm working on learning and contrastive learning, those kind of algorithms.
Good. Thank you. Yeah, go ahead, Abdullah.
Okay, so moving to the...
Hello, Abdullah.
Yes.
Yeah, I have a query. So
yes.
We are designing this adversarial attacks on point cloud network, right? But
yes.
generally in autonomous driving systems, we'll have multiple networks running at the same time. So we'll have for example, if we take Tesla, they are saying that they have around 1,000 networks running parallelly.
Yes.
So how can we apply these attacks in such kind of scenarios?
So in images, there was something called about attacking a pool of networks, not a single network. Obviously, this is very challenging. But in essence, if you can create an adversarial attack that transfer to other networks that are unseen, it should transfer even to 1,000 network, right? As long as they don't work jointly. So if they work all jointly, it will be very difficult to attack all of them. However, I think there are some papers that try to do that.
So what do you mean by jointly, Abdullah? What do they share among themselves?
So sometimes what's called in machine learning, when you have different models and then you basically take the maximum or do like fusion of the prediction, you can actually improve performance. So you can use SVM, linear classifier, and then you do multiple neural networks, and then you just take the maximum prediction, the one which gives you the highest probability to be the prediction that you want. And therefore, you always get better improvement or improvement over all of the methods that are used.
Okay.
If you want to attack all of them, it would be hard. Unless you have access to all of them jointly, you can run the same optimization, but on all of the networks.
Okay. Does that answer your question, Nikhil?
Yeah, I got it.
Thank you.
Okay, great. So people asking questions, that means there are some interest on
Paying attention. Okay, good. Yeah, go ahead.
Yes,
An engaging, yeah, the topic is engaging.
okay. So this second paper, which was also on this year, AAAI 20, tackles, which is joint work with Matthias Muller and Bernardo Ghanem. In the previous examples, even in that ECCV paper, it was about adversarial noise that's added to the image. However, we want to ask ourselves, is this noise meaningful? Which means, does it convey any information about the weaknesses of the network? And another thing is this useful? Is these attacks, adversarial attacks, useful? Can they use them in actual applications? And the answer is mostly no. Like, most of the literature was focused about getting smaller attacks, stronger attacks, better defenses. But everything here doesn't actually really matter when you are talking about a Tesla car or about like a CNN that's used to detect cancer, for example, in hospitals. So in this paper, we tried to look at something called semantic adversarial attacks. Basically, we change not noise on the pixels, but we change meaningful parameters that define the image. For example, in the first row, we change the camera position that's taking that image. You can see that it misses the motorbike as person. In the second one, we changed the track of that UAV or drone, which is autonomously moving, and all of a sudden the drone cannot move properly. In the last example, we changed the weather of a simulator of a self-driving car, and then the self-driving car is not able to move properly. So these are like realistic. Somehow this scenario can happen in real life. You can have a rainy day and your Tesla car would crash. This can happen. So in this paper, there have been some previous works like this paper from CFPR 19, which showed like if you change the orientation and the size and of the 3D object, you can always fool a trained CNN that cannot recognize the object anymore. Like you can see the school bus is not seen in any of the other images. The motorcycle is seen as like, I don't know, parachute or whatever. And the fire truck is not seen in this. So people who are angry about deep learning, they always use this paper and other papers to show like, oh, deep learning is great, but you know, a human would not be fooled by this one, will always identify the objects in no matter how we look at it. So in this paper, we did like a general setup for adversarial attacks that include pixel attacks, which are the famous in the literature, and also includes these type of semantic attacks. By the way, in CFPR 20 and in ECCV 20, there were like, I would say 4 or 5, maybe 10 papers that are all doing semantic adversarial attacks. This one was before, it was in AAAI 20, which was in February, but in June and in August, several papers used the same thing. So we also create a network called BBGAN, or a GAN network that's basically trying to learn a distribution of semantic adversarial attacks. We apply on 3 different applications, EULU version 3 object detector, self-driving cars on Carla simulator from Intel, and then a UAV racing on our own simulator for drones, which is SIM4CV. So the general setup basically goes like this. You have an environment that basically defines everything in your space. If you are doing a simulator, the simulator would be the environment. Your agent A would be the neural network that is running inside the environment or inside the simulation. You have a set of observation that is coming to you. This is O. Action is received from the agent, and the agent receives observation and reward for every action they are taking inside the environment. This is not only for a reinforcement learning scenario or like a simulation scenario. Actually, this setup can work even for classifier. You can think about your environment of the classifier as the set of images, and your classifier is agent A. And the observation is basically the images themselves, and the action is the prediction of the classifier. And the reward is basically the score or the ground truth. So if we think about classifiers in this way, an adversary G is basically trying to fool the agent A by changing the environment. So in a simple adversarial attack that's about additive noise, the adversary is basically adding noise mu to the images X, and then these observations are fooling the agent A, which is the classifier. If you are doing these type of semantic attacks, this mu is, let's say, the weather condition or the camera viewpoint of that environment, and the observation would be the renderings from that environment, and the agent would be doing something, like either detecting the object or predicting the move or the direction, steering direction of the car or the UAV. So this setup actually can work on any adversarial attack. And actually in the paper we show how any of these variables can describe a specific scenario for different scenarios of adversarial attacks. Like if you have a pixel adversarial attack on image classifiers, or you have semantic attacks on object detectors, or on autonomous agents. So in this paper, we propose BBGAN, or learning a distribution of attacks. Basically, we want to learn how or what are the weaknesses of these agents on this semantic parameters, or the parameters that define a meaningful information about the image, like the viewpoint of the camera, or the weather condition of the car, or the track shape that you are driving in. The GAN that we're using is just a simple GAN that has like a generator and discriminator. At the end of the day, the generator would be the adversary, which is shown here, that will be generating or creating these new parameters that will be used by the environment to create adversarial environments that the agent would be fooled in them. So as I said, we apply to
so Abdullah, where does the reward portion come here? Reward, there was a reward in the previous slide, that reward, yeah.
So the reward is used to train the agent.
Okay.
So if you're using classifier, this reward is like ground truth or loss.
Okay, okay.
It's not used by the adversary G. The adversary only uses score Q.
Okay, okay, okay.
So the score, you can think about it as the accuracy of the overall scenario. And then you're trying, using this Q, you want your adversary to learn to generate better or worse mu's that will destroy or reduce the score.
So in the next slide, you showed your contribution, not here, yeah. So the major contribution is you're using, yeah.
So we're using a GAN, we call BB GAN or black box GAN. Basically, this GAN only uses score information of some parameters mu, learn a distribution. Like you can see here, a joint distribution of parameters that if passed to the environment, it will always make the agent fail.
Okay, okay, okay. So that is the contribution.
So this is the bad guy that is trying to make the life of this agent very hard, tough.
Understood, understood. Thank you, thank you.
So actually, we applied 3 applications. As I said, for object detection, we use the parameters define actually the viewpoint and the light direction and the color of the object. We can see that actually our GAN or BB GAN generate adversarial examples that are very realistic and can happen in real scenarios. And the IVUL version 3 detector cannot detect these trucks. Thinks it's like a cell phone or a laptop or whatever.
And BB GAN is trained on which data set?
So the data set is, yeah, this is a good question. If you look at BB GAN, what is the data set? We know that in GANs, we have access to real images. How does the discriminator decide whether this is real or fake? It's a good question. What we do is we use the module called inducer, which is basically like a particle filter that filters different mu's used in the environment and only accept the very worst parameters that the agent scored in and use that as a training. So you can basically do random parameter mu, and then you take the mu's with the worst performance and use it as a training. And therefore your generator or adversary will know or will learn how to create a distribution of very bad parameters. These very bad parameters will be passed to the environment. It will make the agent fail. By construction, all of these parameters should be realistic, which means it's not crazy. Like you can take the viewpoint to be in the infinity, and you cannot see anything from the image. Obviously, this will make the detector fail. But by construction, we constructed this environment such that any parameter mu should generate a realistic observation. Like here, this truck is somehow realistic. I know it has like maybe a weird like blue color or so. Maybe the object detector is not familiar with this color, but it's somehow realistic. Like you can have a scenario where your drone is taking this image and it will not identify the truck.
Got it.
So here we visualize the distribution. Since we are learning a GAN, it can learn a distribution. We can see that for cars, for example, all of these 3 angles and light directions will make the object detector fail. And here are like some simulated and actual real examples. So this is like a toy car. This is my iPhone picture of that car from that angle. You can see actually it has the same misdetection of the simulation.
Correct.
Here we show the carless simulator working smoothly. This is a trained neural network to do a steering on carless simulator. Here an example of like perturbed weather generated by our BB GAN. You can see the car fails in this turn.
Oh,
you don't want your Tesla to work like that, right?
Okay, okay. But the
Yeah.
weather that was simulated is actually just daylight, or is there, maybe I can't view it, is there
So,
rain or
so the
something?
Carla simulator allows you different control.
Weather.
One of the control parameters is on the weather. So they have 4 types of weather. So basically we digitize the real value into one of 4 weathers. And also control the camera. So they allow you to change the view angle of the camera mounted on the car.
Okay, okay.
Yeah, so we learn a setup where basically if you use that setup, you would fail like this. And this is the 3rd application, which is a racing drone. You can see that drone is moving very smoothly. It works very fine. This is our own simulator from our group. Actually came before the AirSim from Microsoft. But then everyone started to use Microsoft and nobody knows about this one, which is unfortunate. But yeah, so here we learn to generate adversarial tracks. Basically, we create tracks that are adversarial, which means if you use these tracks, you will have your network basically failing in these terms. Here we show like how our BB gun can reach very high attack success rate compared to some baselines. We can see that we always get very close, like on object detection, we have success rate of 74 on average. For autonomous driving and for the UAV, we reach very close to 100%.
Good.
3 anchors is just how would you define the track? So a track like this one can be defined in many ways. You can define 3 anchors point that define the shape of the track, or you can define 5 anchor points. And actually, the simpler the track, the hard it is to do attack. So a very simple track that's circle, you cannot change it that much to make it hard. So the success rate would be, so in this, you can see the success rate for the 3 anchors is very small. However, when you have a lot of freedom to perturb your environment, we can reach a very strong success rate. A boost version is just an improved version of our BB gun where we basically use 3 stages of training and we keep track of the best examples from all of the previous stages to improve the performance.
Good. I think there was a question, Shamavi.
Yeah, so we are at the end of this chapter. So these attacks are novel. So our BB gun is not memorizing adversarial examples. The top row is the examples generated by our BB gun, and the bottom row is the closest training example. You can see that our BB gun is generating new or novel examples that are not seen during training and that are also adversarial.
Good, good.
Yeah, this is the code and the paper. This, you can take a screenshot of that.
Yeah. Very good, Abdullah. Yeah, please go ahead with the question. Yeah.
Yes, so this is the end of this chapter. We have only one small chapter left for the last section.
Go ahead, Shambhavi.
Okay, so yeah, I had this question that very recently I happened to read this CVPR 2018 paper, which was which actually generated new black box and white box adversarial attack for optical flow based motion estimation. So did you happen to try this method on those newly generated attacks, or would it be a good idea to try an application based thing of your methodology on those attacks?
Are you talking about the workshop paper in CVPR?
No, I can share the paper link in the chat. It is
it is
called Adversarial Attacks for Optical Flow.
Adversarial Attacks for Optical Flow.
Yes, for optical flow-based action recognition classifiers. So they kind of gave a state-of-the-art success rate on UCF 101 dataset.
Yes.
So did you happen to try or work on that for a comparative analysis?
No, so as I said, like everyone now, every paper is basically doing an adversarial attack on a different domain. So the optical flow domain is completely different from what we're doing here. Here, the goal is actually a very similar paper to this one is the paper I showed here, which is from CPR 19. Basically, we are trying to tackle semantic or physical parameters that define actual 3D space parameters. For example, like the rotation, the orientation of the 3D object, or the rotation of the camera or light, or like in this case, the weather of the car, or like the shape of the track. So it's different than what people do in like my previous paper on point cloud. It was about perturbing the noise or adding, yeah, I remember the paper you're talking about. So actually it's by, I think, what's his name? Like a big professor in the field.
Yeah,
So,
Nath, like he's quite active on Twitter as well.
yes. So,
Abdullah, yeah, I just wanted to ask what is the fundamental difference between optical flow and what you're trying to achieve here?
so optical flow is just, it's just a representation of videos. It's a different representation of videos. Here, I'm not changing, in that paper, they are actually adding adversarial noise, just like the first chapter I showed. Just like this one. They're adding noise like this one to make the optical flow prediction using, I think, optical net or like one of the optical flow prediction network to fail. Here, we are not changing, we're not adding noise, we are changing the environment itself. And actually, if you look at the change is very huge. Look at the image on the right compared to the image on the left. It's completely different image. So you cannot measure it with the L2 norm or L infinity norm. However, this is a realistic change. This can happen in real scenario. And this is what we care about in this paper.
Understood. There is one more question.
There are 3 more questions. Actually, there are 3 more questions in the chat from Zahra. First one is there any relation between semantic adversarial attack and domain adaptation?
This is a very good question. Yes, there is a relation. The community has not merged the two together yet, but it will happen in the future. So people will be using domain adaptation for semantic attacks, and they will be using adversarial attacks for domain adaptation. Actually, one of the most famous domain adaptation methods is called adversarial domain adaptation. And yeah, so it has some adversarial part. However, people now are just investigating these are 2 different phenomena. I would argue domain adaptation is like, at least for now, it's about single output domain. In adversarial attacks, we care about all the possible domains. So find me the worst possible scenario, not only a single target domain, but all the possible domains. Just find me one domain where this network would fail. So it's even more difficult than domain adaptation.
Right. The next question is, in BBM, what is the end result we get from the agent?
So the agent would be predicting the end result. So it depends on the application. So for, where is the table? Here, what's called the score. If you look at the last row, this is the score, or the thing that will be getting, the adversary would have access to this one. For the classifier, it would be the difference between the predicted and the true softmax. For an object detector, it would be the predicted confidence of the true class. So if you are predicting a person, you look at the confidence of the person class of the detector, and that would be the score. And you want to minimize that score by BBGAN. For the simulator, it can be the success or the average success of every episode. So in our simulator, we run 5 episodes, and then we measure how many of these 5 you were able to reach to your target using your autonomous driving. This is very common in robotics papers. They measure the success rate of completing a task by our robot. Yeah, so this can be the score.
Right. The third one is, can we say that BBGAN uses deep reinforcement learning?
The setup, this is also a very good question. All of the questions are very good, actually. This setup is very similar to reinforcement learning, except for the adversary. They don't have adversary. Actually, there is something similar in reinforcement learning, and actually the reviewers always picked on that. But there was a difference, is that they want to train a robust agent using some perturbation on the environment. So yes, there is a relation between reinforcement learning and this generic adversarial attack setup. But this one is more this can include the classifier. Reinforcement learning does not care about classifier, it only cares about like an agent inside a simulator or inside a game. What's called the Markov decision, MDP simulation or MDP process.
Right. The next question is, this is related to your first paper. So have there been any methods that use meta learning to learn a perturbation function which can transfer to unseen networks?
I don't know about meta learning for adversarial attacks, but there are recent papers that actually try to learn a network to create adversarial attacks. And those are conditioned on the input image. So you just do one forward pass for your input, you get an adversarial attack. And these ones actually turn to be working very well, even as a defense. So now people are using deep learning to attack deep learning. Yeah, and this is actually one of the things we use here. We trained a GAN to attack an agent, which is also a deep learning network.
Right. There's one more question. Nikhil, do you want to ask it yourself, or shall I read it out for you?
Sorry?
Nikhil, please unmute yourself and go ahead.
Hi, Abdullah. I have this question. Is the BBGAN rejecting the samples which are not semantically meaningful?
No, it doesn't know whether this is semantically meaningful or not. All what it knows whether it has a low or high score, and that's it. So by construction, the environment should allow only meaningful setup. So we design the environment, right? This environment is designed by humans. It should, there is a range for these parameters mu, such that any mu in that range should be a plausible outcome. So BBGAN doesn't know whether this is plausible or not. It only knows that it has high or low score.
Does that answer your question, Nikhil?
Yeah, I'm still not clear, like how can the environment, because if you change the climatic conditions and all, the environment will change completely, right? So the parameters can.
Yes. You're saying, how do we know that these environments are realistic?
Yeah.
This is actually a good question. There is no well-known way to enforce that. In our paper, even in that CPR paper, maybe this view is just not realistic. It will never happen. You can see that?
Yeah, I can see that.
Yes.
So maybe this bus can never happen in reality. Like this rotated bus on track can never happen. How do you know it's realistic? So how do you expect the network to identify this? This is a very difficult question. It's extremely difficult. And there is it's an open question. It's an open research question. in our case, in our environment, we enforce these, we check these parameters to be all realistic. You can see that this, this one is actually realistic. Like you have a car, you have a somehow cloudy weather, and all of a sudden it's not able to drive. So we made sure that somehow these parameters are realistic, and then we did all of the comparisons on the same space.
Does that answer your question, Nikhil?
Yeah, got it.
Okay, thank you. So our last chapter, I will move a little bit faster now. Since...
Okay. Yes, please do. Yeah. So
this last paper, which won the Best Paper Award at ECCV 20 in the adversarial workshop, which is the only workshop dedicated to adversarial attacks in ECCV 2020. And this one won the Best Paper Award. So this paper is about continuation of the previous paper, but we targeted classifiers specifically. And the observation is that we can see that, for example, this teapot, if you rotate it a little bit, Inception version 3 would not be able to identify the object anymore. And actually, if we plot the confidence of different ImageNet pre-trained networks for the teapot class, we can see that there are some angles that the network, all of them just fail dramatically. So you can see that the confidence drops from 90 or 100% to almost 0. While we as a human, if you look at this teapot, you can identify it while rotating from any angle. We don't find it difficult. It's an easy task. So we want to analyze this, what we call semantic robustness, which is very similar somehow to the previous paper. But here we focus on classifiers, and we develop a new algorithm to do a bottom-up approach instead of sampling-based approach like the previous paper. And we actually do a quantification of semantic robustness of deep neural networks. So this is our pipeline. We use a differentiable renderer to render 3D meshes of specific objects from specific classes Z. We have control parameters, which are the semantic parameters of which we want to analyze. We render images, and then we used pre-trained networks like ImageNet pre-trained networks. And we were recording the confidence of these networks for the same classes of the 3D objects. So in order to do that, we collected 100 shapes from ShapeNet that are from 10 different classes. And all of these shapes are detectable by ImageNet classifiers. So we filtered these shapes in a way such that all of these shapes are identified by the classifier. And then we keep rotating these objects, and we change the viewpoint on all of these 100 objects, and we observe how would the confidence of the networks look like. We see like ResNet, like different from AlexNet, different from VGG, and different from Inception. These are the 4 networks that we analyze. We also changed the viewpoint from the elevation perspective and the azimuth perspective. And we also plot a 2D plot or semantic map that describe how confident is that network. We can see that different networks have different maps for the same object. So this is something new. It has not been observed before in the literature. We can see that these maps can be very different from different network to other networks. And this is what we call semantic maps. So in here, we show how these semantic maps have what we call semantic traps. These traps are basically very low region, or regions that are very low confident, that are surrounded by very confident regions. So imagine yourself using your Tesla detector or whatever, and you find one of these. there can be an accident or a crash, but this crash is very surrounded by a very confident region. It cannot be detected. It's very hard. Unless you do this, you map the entire space of all possible parameters. So there is a scalability problem in plotting these maps. It's very insightful, but it's very expensive. So if you have 8 parameters, like the previous paper, you would need 10 to power 18 forward pass of the neural network to fully map the space, which is very huge. This is like 10 times the number of stars in the universe. Anyway, so this is not scalable. So we want to develop a bottom-up approach such that starting from some parameters mu or u in this case, we want to find the region that is robust, which means it has a very high confidence, has low variance. This is how we define an operator. We call it phi robust. It's an operator to find a region in the space that is very robust. And the goal is to maximize the mass inside the region. The problem, if you used only this objective, the bounds of the mass will always grow. So it would go to infinity. So in order to tackle this, we developed 3 approaches. One is naive. That's basically assuming a prior on the volume of the shape of the space of the region. What's called robust region. Other approaches rely on the ratio between the outer and inner mass, and basically trying to maximize this ratio, or the ratio of the inside mass compared to the outside mass. We developed 2 algorithms. One is black box and one is white box. And basically these algorithms are iterative algorithms. So you just find gradients with respect to the top left corner and top bottom right corner. And this can be extended to any n-dimensional space. So it's not 2D space only. So these algorithms are like using matrices and vectors, can be extended to any dimension. Here we show how our iterative algorithms can work to detect these robust regions. You can see they converge when they reach, like they cover the robust region around that initial point. Here we show some results on 2D. We use one application of these robust regions. Basically, if you take the expected value of the volume of these robust regions in the entire space, and you normalize by the total volume of the space, you get a number. This is what you call server, or expected robust region size, or semantic robustness volume ratio. This basically gives you an estimate of how robust is your network in that space. We benchmark different networks in this using this metric or measure. We notice that ResNet 50, even though it is less accurate on ImageNet compared to Inception, it is way more robust than Inception version 3. And this is one outcome of this paper, which is this very weird observation. Actually, this observation is also justified by the maps that we show in the paper. You can go and look at them. Another application is that if we average all of the maps, we get a sense of the data bias in ImageNet. Because this maps is the average of all of the networks, of all of the shapes for that specific class, for the cup class. We can see that all the networks agree on this structure, which means this is a data problem. The data are like focused on this region and on this region. So obviously all of the networks would fail in the middle region.
Abdullah,
this is basically it. This is the paper. So now,
Abdullah, how did you tackle the scalability problem here? That which slide? Scalability.
So the problem, as I said, like if you go here, if you want to plot these maps, it's fine for 2 parameters, but if we have 8 parameters, you will have 8-dimensional space. You need to plot it with so many forward passes. So to tackle this, we define a bottom-up approach. This approach is irrespective of how many dimensions you have. You can see that these formulas are like one step, no matter these matrices and matrix and vector multiplication does not depend on the size of the dimensions. So you can always do iterative algorithm to grow these regions inside the n-dimensional space, as you can see here, and it will converge. It will reach to a place where it will stop growing, and then you know that this is a region in the n-dimensional space that is robust. You can repeat this with different initializations, and you can basically get an idea of what are the robust region and what are the not robust region in the space. So it doesn't fully capture the space. However, at least in this application, it can give us an indication of how robust overall is the network.
Good. Very good explanation, Abdullah. So yeah, any questions, please go ahead. So Abdullah, are you done with your thesis? Are you now writing your thesis or what?
Actually, this presentation can work like a thesis.
Super. Spectacular.
Yeah.
Good.
But I'm still working like on research right now, so yeah.
Good, great work. Very good explanation. Others, we're almost we'll let Abdullah go with few questions. If you have, please go ahead.
Yeah, so I'm done with my presentation. If you have any questions, please ask. Here are my contacts. You can find in the website you'd find my phone number, my email, everything. You can also contact me using this Twitter or the GitHub people.
Good. Abdullah, and while formulating your research problem, what was the phases that you went through while you focused on this area? Did you go through a general review, or was this problem given to you? How did it come about?
So it started with this. So actually the order of papers was this one. This one, the AAA paper. Actually, it was rejected in CPR in ICCV, and it was accepted in AI. But the idea was, this was the intuition. Yes, adversarial attacks are great, but they're not useful and they're not meaningful. So this was even before any other paper, like even before this one, even though this one got accepted before us. I think we are I would say among the very early papers that looked at this problem for semantic adversarial attacks. We actually coined the term semantic adversarial attacks. The first version of this paper appeared in 2018, in December 2018. So it was way before all of these other papers.
Understood.
Yeah.
So that is how the idea developed, and you continue with that.
Yes. So after this paper, we noticed that it's not scalable to just do random sampling and filtering. So this paper came into practice, which is this one about bottom-up approach. And then we moved to this point cloud business because there was interest in the community on point clouds. Yeah, so this is how the order of things worked.
Okay. Yeah, and before we let you go, one last question. Obviously, I'm assuming you review papers as well for other conferences.
Yes.
So what do you look for in the papers, and what are any checklists do you have, or what do you look for in any paper?
So usually I have I reviewed for CPR, ICV, and SCV. I'm also reviewing for the coming iClear and CPR. Usually how I look at, first of all, is the paper tackling a well-known problem or not. If the paper is inventing its own problem, this is a red flag. So if it is doing image classification or object detection, it's an easy to review paper because you can basically look how novel is the algorithm and how good is the results. And then also how well is the paper written and presented.
Got it.
If it is well presented, if it's a novel idea, if it's an interesting idea, and if it works well, and if it is correct, because sometimes people invent new things that are not correct. Even if they get the best results, if you invent something that's not correct, there is a methodological error, then this can be rejected, even if you have the state-of-the-art result.
Understood. Good,
So it's very simple, like how novel is it, how correct it is, how well written and presented it is, and how good is it working on a famous benchmark. So sometimes people use not famous benchmark, like they use a not well-known data set. This is also a red flag. Why didn't they use MNest or ImageNet or, well-known data set?
Good. Very good, Abdullah. Yeah, thank you very much for such. Yeah, we'll let you go now. Others, please contact Abdullah via email. He's available on Twitter. And hopefully, when are you planning to defend Abdullah?
I don't know. Maybe not.
Difficult question to answer, I know. Okay. Yes, Shambhavi.
Yeah, no, that's done.
Okay.
Probably the longest talk ever.
Very good, Abdullah. Very good work. Hopefully, are you targeting any journals as well?
Yes, so I might combine all of these papers in one journal paper. Maybe what's called the TPAMI.
Good.
Yeah, so this was on the plan also. But now I'm busy with CPR. CPR is in 1 month and it's a very tough conference.
Good.
Yeah, we have a policy of only submitting to top tier conferences. Like, if you just want to publish in anywhere, you can always publish. However, if you want to publish meaningful work, you should publish only in CPR, ICCV, ECCV, iClear, NeurIPS, or ICML, or AAAI. But other than that, you can get easy publication, but you will not get citations and you will not create an impact on the community. And that's what you should be aiming for. Yes.
Since you mentioned citations, what is your take on review papers? I have, being an undergrad student and completely new to research, I have observed that generally review papers get lots of citations in a very short span of time. Is it a good idea?
Yes, but a review paper, you cannot publish it in CFPR. At least,
right.
I've only seen one paper in CFPR that is a review paper. And even that, it wasn't about only review, but they did a lot of experiment. They did basically benchmark all of the algorithms that appeared in a specific domain, which was adversarial attacks, actually. So there was a review paper about adversarial attacks in this CPR 2020, but they did a lot of experiments. They experimented with every possible algorithm on adversarial attacks. And then they showed results and which one is better. And this is actually very useful. So it's not about only review, but it's also benchmark. So if you can do both, like review and benchmark, you did implement all of the previous algorithms on the same data set, on the same setup. Yeah, this can be published. It will get a lot of citations. But like the papers I showed about adversarial attacks, the first papers I showed on adversarial attacks, those papers have like 2,000 or 3,000 citation, and they are not review papers. Those are the first papers on adversarial attacks. So.
Yeah. Oh, there's one question by Zara which I missed. Sorry. Does semantic attack, is it more domain generalized or can tackle different domains? Semantic attack. That's the question. Can it be generalized is the question.
I don't know. I don't understand the question properly.
Okay.
So
Probably, okay, it's fine. Zara, you can reach out to Abdullah. He is pretty easy to find over Twitter also. So I think Abdullah will let you go. Thank you very much for your time. We greatly
you,
appreciate
everyone.
your time.
Thank you, Mishrash. Thank you, Jamaija. And thank you all for hosting me on this. And maybe we'll
We
meet.
wish you all the best. Yeah, we will expect more papers from you and hopefully do great work after you graduate as well.